In this next screencast, we discuss properties of exponents. In order to work with exponential functions effectively, it's important to know how exponents can be manipulated. In Chapter 1, we introduced the following 4 basic properties of exponents. First of all, if you have a quantity a raised to the p times the same quantity a raised to the q, you can calculate the answer by taking a and raising it to the p plus q. If you have a to the p divided by a to the q, you can calculate the answer by simply taking a raised to the p minus q. If you take a number a and raise it to the 0 power, you always obtain 1. And if you raise a number a to a negative power, we define that to be 1 over a to the p. Of these properties, this is probably the one that's least intuitive. We discussed it back in Chapter 1, and you have used it when you've worked with scientific notation. Just a reminder, if you had, say, 10 to the negative 1, what that means is 1 over 10, according to this definition, which of course is also written as 0.1. If you had 10 to the negative 3, according to this definition, this would be 1 over 10 cubed, which is 1,000th, or 0.001. So that was supposed to be just a reminder of how you've used this previously. In this section, we're going to continue our discussion of exponents and introduce 5 additional properties, and we're going to begin with 3 of them. So let's look at this first property. If you have a number a raised to the p power and then you raise the entire thing to the q power, you can calculate the result by really just taking a and multiplying it by the product of the 2 powers. In this column, I have a motivating example to help you think about why this result should be true. Suppose I took 10 and raised it to the 3rd power, and then I took the whole result and squared it. Well, what we're doing is squaring 10 cubed. So that means we take 10 cubed times 10 cubed. Well, right here is 10 cubed, and here's another 10 cubed. And I'm squaring it, so I have 2 of them. But really all we're doing is we're multiplying 6 factors of 10 together, and so really this is just 10 to the 6. Notice that the 6 could have been obtained by multiplying the 3 and the 2. Let's look at the next property. This says if you have a product of 2 numbers raised to a power, you can calculate the product also by taking each factor of the product and raising each one of them to the power p and then multiplying. Let's look at an example to see why this ought to be the case. If I take 4 times 10, that quantity, and I square it, really what I'm doing is I'm taking 4 times 10 and I'm multiplying it by itself twice. That's what it means to square. But really, if I look at this, I'm just multiplying 4 numbers together. 4 times 10 times 4 times 10. The associative and the commutative properties of multiplication say we can perform these multiplications in any order we like. So we could multiply the 2 4's together and the 2 10's together, which would give us 4 squared times 10 squared. So that illustrates this property here. Finally, if I have a fraction, a over b, that's raised to a power p, I can calculate the result by taking the numerator and raising it to the p, taking the denominator, raising it to the p, and dividing. So let's see an example. If I were to square 5/7, squaring 5/7, that means I take 5/7 and I multiply it by itself twice. but we know how to multiply fractions. We multiply the numerators and we multiply the denominators. That would of course give us 5 squared over 7 squared. So you can see, again, an application of this property. Let's have a look at the example below. In this example, we will practice using the properties that you've seen to date. So in example A, we are taking the number 3 and raising it to the negative 2 power. Think about what property would be useful here. If we scan the properties that we've got, this property seems like it would be the useful one because it tells us what it means to raise a number to a negative power. So if we scroll back down here and we apply that property, we arrive at 1 over 3 squared, which of course is 1/9. Let's look at B. Here we're taking a number y and squaring it, and then we're taking the entire quantity and raising it to the 5th power. That looks like what we were doing in this property. And so we ought to be able to calculate the result by taking y and raising it to the product of the two powers. So we get y to the 10th. Now let's look at part C. This is a more complicated fraction, but if we look at it, we can see one place we can begin. There's this one section up here where you have u cubed raised to the 3rd power. That we can simplify immediately. U cubed raised to the 3rd power should remind you of this property right here because you have a number raised to a power raised to another power. So you should be able to simplify this by taking u and raising it to the product of these two powers. This is multiplied by v squared, and the whole thing is divided by u to the negative 2 v cubed. In the numerator we have u to the 9th v squared u to the negative 2 v cubed. Now you can see that the numerator and denominator both involve factors of u, same with v, factors of v in both the numerator and the denominator. We should be able to do some simplification. First of all, let's separate the u's from the v's. I'm going to rewrite this as u to the 9th over u to the negative 2 times v squared over v cubed. So now we can simplify each fraction separately. If you have u to the 9th divided by u to the negative 2, we have a property that can help us, namely this property here. If you have a number raised to a power divided by the same number raised to another power, you can calculate the value by taking the number and raising it to the difference. So that is precisely what we would need to do here. So we take u and raise it to the 9 minus negative 2, and for the v's we take v and raise it to the 2 minus 3. When we do this, we arrive at u to the 11th v to the negative 1. Now, this is fully simplified. However, it's not a very friendly looking answer. Most people would be uncomfortable looking at v to the negative 1. Many people would wonder how to interpret that. So usually when you are writing your final answer, it's best to leave all of your values having positive exponents. So let's rewrite this v with a positive exponent. So I'm going to rewrite the u to the 11th this way. I'll write it as u to the 11th over 1. And this is multiplied by v to the negative 1. But v to the negative 1 is 1 over v to the 1, or rather 1 over v. Now, if I multiply these two fractions together, I get u to the 11th over v. This would be the preferred way of writing your answer. More people will understand how to interpret this than they will understand how to interpret this. Now let's go ahead and look at part D. If we look at the quantity that's inside the parentheses, we should be able to use some simplifications in there. That will make it easier ultimately to square. 8 and 6 share a common factor of 2. So I can rewrite the 8 as 4 times 2, and then we also have the 10 to the 4th. 6 is 3 times 2, and then that is multiplied by 10, and the whole thing is squared. We can cancel the common factors of 2. Notice there's a common factor of 10 in the numerator and the denominator. That could be canceled. That would leave 3 factors of 10 in the numerator. Alternatively, you could take 10 to the 4th and divide by 10 to the 1 and use your exponent properties. You would take 10 to the 4 minus 1, which is 10 cubed. So either way, you would arrive at 10 cubed. So we have 4 thirds times 10 cubed squared. Now let's go ahead and do the squaring. If you recall, when you have a product raised to a power, as we did in this property right here, we had a product raised to a power. You can raise each factor in the product to that power to calculate the final value. So here we can take the 4 thirds and square that, and take the 10 to the 3rd and square that as well. Squaring 4 thirds means that we're taking 4 thirds times 4 thirds, and 10 cubed squared, we can use an exponent property here. That would be 10 to the 3 times 2. And now let's perform the last multiplication. Multiply these fractions together. 4 times 4, 3 times 3. So we have 16 over 9 times 10 to the 6th. And you could leave your answer in that form if you wished. Okay, now let's go ahead and look at example E. Here we're taking 2 times 10 to the 5th and multiplying that by 3 times 10 to the negative 6. Despite the parentheses, all we're really doing is multiplying 4 quantities together. And again, the associative and the commutative properties of multiplication suggest we can perform these multiplications in any order we like. So we can multiply the 2 and the 3, and we can multiply the 10 to the 5th by the 10 to the negative 6th. 2 times 3 is 6, and to multiply 10 to the 5th by 10 to the negative 6, we can add the exponents. And so, sorry, that's multiplication there. And we get 6 times 10 to the negative 1. Again, this is fully simplified, but we would want to give our answer without this negative exponent. So let's rewrite this as 6 times 1 over 10. This is 6 times 1/10, which is 6/10, or you could write this as a decimal, 0.6. Okay, let's move on and look at section 9.3, roots and exponents. There are 2 remaining properties to discuss. These properties relate exponents to roots. However, before we can discuss these properties, we need to introduce roots. So with that in mind, let's look at example 9.6. Complete the following table without using a calculator. You don't need to complete the cells marked with an X. Go ahead and pause the recording at this time and complete the table on your own. Then continue playing the recording to check your work. Okay, let's go ahead and complete the table. In the first row, we're raising 2 to the powers 2, 3, 4, 5, and 6. 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16, 2 to the 5th is 32, and 2 to the 6th is 64. In the second row, we're taking -2 and multiplying it by the powers 2 through 6. -2 squared is 4. -2 cubed is a -8. -2 to the 4th is 16. -2 to the 5th is -32. -2 to the 6th is 64. In the third row, we're raising 3 to higher powers. 3 squared is 9, 3 cubed is 27, and 3 to the 4th is 81. In the next row, we're multiplying -3 to higher powers. So -3 squared, that's 9. -3 cubed is -27. -3 to the 4th power is 81. Next row, 4 squared is 16. 4 cubed is 64. -4 squared is 16, but -4 cubed is a -64. You'll probably find it helpful to refer back to this table in the next few examples. So let's go ahead and look at example 9.7. Determine the missing numbers in each of the following equations. So let's look at part A. Try to determine what number cubed would give you 27. In other words, what number multiplied by itself 3 times would give you a 27. Well, there's only one such number that can do this, and that would be a 3. So that number sitting in there must be a 3. Go ahead and pause this recording and work through parts B, C, D, and E, and then continue playing the recording to check your answers. Okay, let's go ahead and look at part B. What number raised to the 4th power would give you 81? Well, here there are actually 2 numbers that would work. 3 to the 4th power gives 81. You can see that from the table up here. Also, -3 to the 4th power also gives you 81. Now let's look at part C. What number squared would give you 64? Again, there are 2 numbers that could work, 8 and -8. Now let's look at part D. What number raised to the 5th power would give you a -32? Well, the only number that would work in this case is a -2. And so that's the one we're looking for. Finally, part E. What number squared would give you a -16? So what number multiplied by itself twice will give you a -16? In this case, it's impossible. There's no real number which, if you squared it, could generate a negative quantity. Because you know when you square a number, you always arrive at a number that's positive or possibly 0. So, no real number exists for this one. The missing numbers that you were looking for in the last example are called roots. For example, 3 is the cubed root of 27 because because 3 cubed gives you 27. 8 and negative 8 are square roots of 64 because negative 8 squared gives you 64 and 8 squared also gives you 64. Negative 2 is the fifth root of negative 32, and that's because negative 2 to the fifth power gives you negative 32. In general, an nth root of a number a is the number which, when raised to the nth power, equals a. In other words, the nth root is the number which, if you raised it to the power n, you would get a back. So let's try out our understanding of roots on the next example. Example 9.8, find the indicated roots of the following numbers. In A, what are the square roots of 36? Well, what we're asking is what number or numbers squared will give you 36. The numbers that sit in here are the square roots of 36. Well, you can see that there are two of them, 6 and negative 6, both work. So those are the square roots of 36. Let's look at B. What are the cube roots of 8? In other words, what numbers, when cubed, give you 8? Well, in this case, there's only one number that works, and that's 2. How about part C, the fourth roots of 81? Here we're looking for numbers which, if you raise them to the fourth power, would give you 81. In this case, there are two such numbers that work, 3 and negative 3. Now let's look at part D, the cube roots of negative 64. Well, those numbers would be the numbers which, if you cubed them, would give you negative 64. In this case, there's only one such number that would work, and that's negative 4. Before moving on, notice that sometimes there's only one root, and sometimes roots occur in pairs. In general, when you're calculating even roots, like square roots or fourth roots, in other words, where these powers are even, those kinds of roots, the even numbered roots, they always occur in pairs. The odd numbered roots, like cube roots, there's always going to be one of them, but even numbered roots occur in pairs. Now let's go further into this conversation. We denote the nth root of a number a by this symbol. This symbol here is called the radical symbol, and sometimes people refer to this as radical a, but we think of this as the nth root of a. So this is the notation that we use when we talk about roots. Now, there are two important things to understand when it comes to using this notation, and I have them bulleted here. First of all, for even numbered roots, like in the scenario up here, for even numbered roots, in other words, square roots, fourth roots, sixth roots, eighth roots, this symbol refers to only the positive root. So again, remember, when you're talking about an even numbered root, there's always a pair of them. One of them's positive, one of them's negative, just like here as well. In that case, this symbol refers to only the positive root. Otherwise, if it's an odd numbered root, this symbol refers to that one root. Secondly, when we're talking about square roots, people generally do not put the number 2 on the radical symbol, and instead they just write the radical symbol without any numerical value. So anytime you see a radical symbol like this without a numerical value, you assume it's a square root. So let's practice working with this new notation. Example 9.9, find the indicated roots. In part A, you are being asked to determine the cubed root of 64. In other words, you're trying to find the number which, if you cubed it, would give you 64. Is there such a number? Yes, and it's 4. So the cubed root of 64 is 4. Now let's look at the next one. Here we're calculating the square root of 25. In other words, we want to find the number which, if we squared it, would give us 25. Well, remember that both 5 and -5 would work here. But in this case, we're talking about an even-numbered root, and this symbol will represent only the positive root, just the 5. So we say the square root of 25 is 5. Next, part C, the fourth root of 16. In other words, we're looking for the number which, if you raised it to the 4th power, would give you 16. There are two numbers that work, 2 and -2. But again, in such cases as this symbol references the positive root, and so we write 2. Let's look at part D. Now we're being asked to calculate the square root of -81. In other words, we're looking for a number which, if you squared it, would give you -81. Well, there is no real number that can do this, because if you square a real number, you always end up with a positive quantity, or possibly 0. So here, there's no number that can do this. So we will just say that this does not exist as a real number. E. Now we're wanting to know the cubed root of -27. In other words, we want to know what number cubed would give a -27. Well, there's only one number that will work here, and that's a -3. So the cubed root is -3.